Hello. Just press once to briefly. Is it green? Yeah.
Yep.
Ah, yeah. It's there.
Okay, time to get started. So I'm Matt. I'm the systems manager at Weta Digital. So I run the team that runs all of our servers and our storage and our networking. And I just wanted to give you guys a little bit of an overview of some of the things that we found using Python, basically during Avatar, which is when it sort of really kind of came into its own at Weta. That was really driven by the fact that we assumed everything used to be Perl, but Maya, which is sort of the artist's primary tool, embedded a Python interpreter in it a few years ago instead of using their own language, Mel. So a lot of the pipeline artists have started using Python, and there's the day-to-day thing that's crept into other parts of it. We actually run the largest supercompute cluster in the southern hemisphere. We had about 36,000 cores to render Avatar. That was divided up into about 17,000 job slots, so we could run 17,000 jobs simultaneously, 24 hours a day for about 2 years. This is kind of a made-up statistic, but I imagine we probably run the Python interpreter more times per day than anybody else in the country. I don't have proof of that, but if anybody thinks they do it more, let me know. So we run it millions of times a day. And what I really want to focus on is sort of its use as a system administration tool and kind of in our job pipeline. So I mean, Python really, in a lot of ways, is a better Perl. And Perl was really, going back in a lot of ways, a better. Does anybody remember what Perl replaced?
Better Welsh?
Awk, that's right. But it turns out that Python isn't really a great awk. So I'll talk through a couple things that we found. I don't know if you guys can read all that. So this is basically some strace output from a job starting up, looking for the pthread library. So this is the Python interpreter looking for the pthread library. And this isn't really Python specific, but I'll show you kind of how we optimized it. So the way we do everything is all our libraries are loaded on the network. We have too many machines to do local installs and try to keep track of everything. So anytime we install new software, it's installed over the network. So when we look for libraries, oftentimes we're looking over the network. So all these paths starting with wall, that's a network location. And all these things. So someone in this environment is using Subversion and SQLite and Tickle for something. Who knows what else? So it searches everywhere for it until finally it finds it. But you can see as part of this, like the trailing end of the path. So it looks in lib, and then libTLS x86-64, which is the 64-bit architecture. Doesn't find it there. Tries it just in the libTLS directory. Doesn't find it there. Tries lib x86-64, still doesn't find it there. Finally just looks in that lib directory, still doesn't find it there. Okay, moves on to the next location. They'll do that everywhere. So you can see the e-no-ents on the right side, no such file or directory. It never finds it in any of those locations. This is an optimization that they put into Linux. A so-called optimization. So you can have architecture-specific shared objects. So it looks for your architecture. The only thing we've ever seen use this are NVIDIA drivers. But meanwhile, it's looking over the network millions and millions of times a day for architecture-specific libraries that will never exist. So all you have to do, if you touch this file in Etsy, HWCAP is like hardware capacity or whatever they name that feature. The dynamic linker, if you strace any executable opening up, the dynamic linker first checks to see if this file exists. And if it does, then it never checks those subdirectories. So the easiest thing to do is touch this file. If you have NVIDIA drivers, just symlink your correct architecture into user lib, where it'll look for it, and then be done with it. So once you do that, it greatly simplifies the search path. You can see it just looks in whatever directory lib and then doesn't find it, it moves on. It really cuts down the amount of loading of shared objects that you have to do, which depending on your version of Python can be quite a few. So this brings me on to another problem with loading Python. I mean, one of the things we were seeing was that Python would sometimes take 10 seconds to start an interpreter. When you're running it millions of times a day, that's a really long time. So we really had to trace down, like, why does Python take so long to start up? And this is kind of where I was saying it's not really a great all. I mean, you don't think twice of building sort of large, command pipes on the shell, pipe to awk, pipe to grep, pipe to sort, then pipe to Python. Oh, okay. 10 seconds later, that interpreter starts up and then finally does something. So this is an example of what sys.path looks like on one of our interpreters. This is actually shortened. So we have some site packages, a whole bunch of different places, and all these eggs. So every egg that's ever installed. So there's 192 things in syspath. And every time you do an import, it looks in every one of those locations until it finds it. So eggs actually really kill performance. So keep in mind that every one of these directories is on the network. So one of the nice features of importing is that not only will it look in directories, it will also look in zip files. So zip is a little bit of a weird format, especially on a Unix system. It's more of a Windows thing. But one nice thing that zip files have that other formats don't, like tar or something, is that zip files basically have a manifest header that lists all the files in it, where tar doesn't. To see if a file's in a tar, you have to actually seek through the entire contents of it. So if you put a zip file, like there in the middle, we have all apps Python 251 zip, which is essentially the zipped version of Python that we have lib python 25.zip. We've zipped up the entire standard library and all the eggs and everything, and just put it in a zip file, and cut all that out of syspath. Now it's only 15 things. All it has to do is it finds that one file, looks in it, grabs the header out, says, is this module that I'm looking for in there? Yes, no. Okay, done. It's a little bit more CPU overhead, but CPU is cheap. Network latency is huge. So just here's a quick comparison. You can see it opens, and then the sort of red one, so blue are the number of opens that starting up a normal Python interpreter does in our environment. They'll do over 3,000 open calls. Also, like about 3,200 open calls. Over 3,000 of those are file not found. It's just looking, do you have this? No. Do you have this? Is it there? Is it there? No, 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 no. One of the things is on a network file system, a lot of times negative entries aren't cached. So if you ask the file server, do you have something in this directory? It says no, and then it forgets about that request. Because I guess when you think about it, I mean, you have a typical directory that has 10 things in it that it can cache. The number of things not in that directory is essentially unlimited, right? It's every other valid file name minus the 10 that are in it. So it's not going to sit there and cache just random requests for files that it doesn't have. So those can be really slow. So when you sit there and you ask all day long, like for non-existent files, none of that information tends to get cached. And then once it does tend to find the files, it tends to do a lot of things like stats to find out the access times and things like that. A lot of that comes down to like it's looking for PYC files, which we'll see later. But it has a much better, by the time it gets to doing stats, it has a much better idea of whether the file exists or not. So a much smaller number of those result in file not found. But you can see the difference anyway between going from just a standard Python install, the number of syscalls that it takes, down to having a zipped version. So even doing something like not even doing your eggs or anything, but even zipping the standard library and putting it in a single file instead of using site packages or all that stuff results in a huge savings. Now you can imagine, like on a good day, these calls are really, really fast. But let's say it gets to be busy, and let's say each call takes a millisecond. You know, you're doing 3,000 open calls that now take a millisecond. A millisecond is still pretty fast, but over a busy network, you know, that's not unrealistic on a millisecond. So there's, you know, 3 seconds doing opens, another 3 seconds doing stats. So now your interpreter is taking 6 seconds just to do the system calls that it takes to get you to having a running interpreter. So zipping things really optimizes it. So this is looking for a non-existent module. This is basically watching an S-trace. What happens when you type like import bork? Looks for a file called bork. It looks for an SO called bork. It looks for bork module.so. You never see those. It looks for bork.py, and then finally bork pyc. And then it starts looking through everything in, so it looks in the current directory first, then it starts looking in everything in your sys.path. Which again, every egg that you install adds itself to sys.path. So now it's going to look starting there, and then all the way down, you know, to the final one, and then finally it'll say thousands and thousands and thousands of syscalls later, it'll say no module bork. So the best thing you can do really for this kind of thing, it's difficult to do though because egg is such a standard, but it's to actually pull things out of eggs and just put them into site packages or put them into your project directories directly. But the way that eggs have been implemented is actually really slows down starting things. The other problem that we run into sometimes is with the PYC files and bytecode generation. Because we're on a shared file system, we at any given time are running probably 3 generations of the Python interpreter on probably 2 architectures, on 32-bit and 64-bit, and occasionally on Windows, which is reshared through Samba to a small Windows cluster that we have. So what you end up with is all the interpreters sort of fighting. So if you have a common code module, let's say, that somebody writes for the company and puts in a standard shared location, somebody loads it in 2.5, it says, wow, there's no 2.5 PYC, I'll go ahead and make one. Then somebody loads it in 2.6, and then they'll say, wow, that PY is out of date, it's for 2.5, I'll go ahead and recompile it for 2.6. Then somebody loads it in 2.5 again, and then it blows away the 2.6 one. And then somebody loads it in Windows, and it does something really weird sometimes, which is just refuses to run because it says there is one, but I can't load it for some reason. I don't know all the details of this, but apparently, like the bytecode, even between the same version, I think on different architectures, isn't compatible. And in certain cases, it'll cause it just to bail out instead of it'll think it's corrupt or something like that because it's from Windows and you're on Linux or vice versa. So in 2.7, they added some options not to write it. Before we had to do things like really lock down permissions and have a whole special set of tools for publishing code that had permissions to do this, and you would just try to keep the user's interpreters from having write permission to the directories. But then occasionally, again, somebody would run something as administrator on Windows, write out a Windows 32-bit PYC file, and then the whole Linux cluster would all of a sudden start losing their optimized version. So there are 3 ways to do that. Python-B, you can set the environment variable, Python don't write bytecode, or from within Python itself, you can set sys don't write bytecode, and you can do that dynamically while the interpreter's running. But bytecode generation, I mean, it saves you a little bit of time at the startup of the interpreter, but it costs you a ton of time in just lost work, and constantly having things start up and having to write bytecode. It also makes the interpreter startup sort of not repeatable, right? So sometimes you can start an interpreter, it'll take this many seconds, and other times you'll start it up and it decides to write out bytecode, which takes a lot longer. So you can't just rely on something running. I really actually consider the whole bytecode thing kind of a missed feature. And I mean, so this happened in 2.7. Before that, we were looking at sort of disabling it altogether. But the sort of grumpy sysadmin in me tells the coders, like, the interpreter is the baseline. when programmers come to me as a sysadmin and say, actually the interpreter does some things we don't like, can we fork a copy of the Python interpreter? It's just the interpreter is just the baseline of everything. If the interpreter doesn't do what you want, you chose the wrong language. Go pick another one. But so there is a PEP out there, 3147, which proposes a whole mechanism of dealing with having multiple versions of Python, writing out bytecode. This didn't come out very well in the sort of PDF version, but basically their example of the top one is a directory that has a bunch of stuff. You end up writing out these version files into another subdirectory. So you write a version file for each version of the OS that you have, which again looks eerily similar to this, which was a terrible idea. So it's again going to actually increase the amount of calls made out to the file system, because now it's not only looking for PYC files, it's looking for, do you have a subdirectory called this? Yes, is there a PYC file in it? So those are some of the things we sort of came up against: zipping things and turning off the hardware cap thing were actually the biggest wins we had, and really cut down the startup time from something like 6 to 10 seconds back down to something manageable. So that's all I have. Well, I have more, but I don't have time. So does anybody have any questions?
Don't you find you have a thundering burn problem with the NFS servers when you say bring up a new job of 2,000 cores and your NFS server suddenly melts to the ground?
Yeah, we do a little bit, especially when the interpreter decides to make thousands and thousands and thousands of calls.
Wouldn't it be easier to ship the binaries out to the cores, out to local disk?
It becomes it's a trade-off of kind of performance and management, right? So
it's automatable though, I guess.
Yeah. So we inevitably run into problems with that, managing the number of machines we have. So yeah, we like to keep everything on the network.
Anybody else? Yes.
Yeah, just wondering how big the impact might be if you touch, like, this very interesting, and if you're using it for your, I don't know, just private server or private purchase. I mean, you guys are using probably most of the things over the network, but apparently if you're using it privately, it's only microseconds, but maybe it also increases over.
If you look at the history of some of this stuff, you'll see that there have been so many workarounds for sort of slow interpreter startup. I mean, all kinds of things like mod Python or something are these really big sort of infrastructural hacks around the fact that you could do CGIs fine. Like Python CGIs are amazing. But if it takes 5 seconds for the interpreter to start up every time you call a CGI, it kills it. So it's like, well, let's write this Apache module that then keeps a running interpreter, but then you have all these other problems that come along with it of like, how do you get modules to reload and everything else. Like all these problems go away if you just have CGIs, right? Because everything comes up and runs and then exits cleanly. So I mean, it's not just us, but there's been all kinds of work around the fact that interpreters are slow to start up, instead of kind of attacking the problem, which is like if we make the interpreter fast to start up, then a lot of things go away. So I think it is valuable even for people that aren't running it millions of times a day. I mean, you do see it.
I mean, it's a basic point, but I think if you use pip to install your Python libraries, then it installs them flat. It doesn't install them in eggs, so you don't end up with a system file being 200 elements long. You end up with it being like 10 or something instead.
Yeah, there are. I mean, we've been moving away from eggs, but
I guess the zip file kind of solves the problem for you to some extent.
Yeah, I mean, I picked that as an example of why eggs are sort of horrible for this kind of thing. But that's how people like to ship things. I mean, if you still look for Python modules online, the instructions are always, install this egg.
sounds like you need to hit developers with a slightly bigger stick.
Yeah.
Continuous design installation. No.
Get the developers.
It's usually down around a second or two, yeah.
Any other questions to Mac? No? Then
All right,
thank
thanks
you
for your
very
time.
much for this interesting talk into dimensions that most people don't even see or are aware of when dealing with PyCon. So thanks a lot. Tim, I guess he's still next door. So I've got a second. Unless you want to fill in some things you didn't have time for, because Tim is probably still.
Is that, I think that might be Graham Dumbledore, so I think he's still next door.
Okay.
Yeah.
Well, no, that's my
I'll
voice,
leave
that's
it-
the mini DB.
I'll leave it here with the projector.
Yeah, if you want to fill in on something until Tim comes over. This was the next one.
Yeah.
So you might as well just.
Oh, it's yours.
Yeah.
Cool. Thanks for that.
The next speaker. Track.
Let me think. I'm out of slides.
No, the lecture is gone, but if you just want to speak freely about it or whatever.
Yeah.